Imagine remotely explaining something to someone, and automated visual guidance appears on top of your verbal instructions. We present Speech-to-Spatial, a framework for grounding spoken utterances in a live, shared view using augmented reality. Our framework disambiguates spoken instructions in remote assistance scenarios, making collaboration more seamless. Traditional remote assistants relied primarily on verbal interaction. A novice user would call a remote expert, often over a phone line, and resolve the issue through conversation alone. With the rise of smartphones, the industry has shifted toward video-based assistance. Users can now stream their view through their phones, allowing remote experts to visually understand the context of the problem. More recently, augmented reality has begun to attract attention as the next step in this evolution. Experts can mark areas of interest using visual annotations, and novices can view these annotations directly through AR-enabled devices. However, this transition has been slow. From phone-based to video-based assistance, and even AR-based solutions still rely heavily on manual annotation by experts. This dependence limits scalability and prevents truly seamless remote assistance. To address this challenge, we present Speech-to-Spatial, an end-to-end framework that disambiguates spoken instructions, reducing the need for manual object indication during remote assistance. Our approach uses a graph-based representation, specifically a scene graph, to model spatial relationships among objects in the shared view. This representation enables the system to infer the object the remote expert is referencing in coordination with spatial referring expressions in natural language. We report findings from a formative study on human speech patterns, use these insights to inform system design, and then quantitatively and qualitatively evaluate the benefits of our disambiguation pipeline, demonstrating its potential for remote assistance. Our pipeline begins with a remote expert's verbal instruction. The local user streams the view from their AR device to the expert, who then issues a query, such as, "Look for the blue quest box below the black thermos." We first extract linguistic attributes from the spoken instruction and identify intrinsic object properties in the description. Any distinctive attribute, such as color, size, shape, or texture, is used to narrow down the target object. In this example, the key attribute is the color black. Next, we extract relational properties from the instruction, such as spatial relationships between objects. We determine whether the target object is anchored to another object. For instance, the below relationship between the target, the quest box, and the anchor object, the thermos. If the instruction includes references to prior mentions, such as the object I mentioned earlier, we retrieve the corresponding interaction history using our graph-based representation. We illustrate this memory mechanism in more detail in a later slide. Then, we merge these intrinsic and relational attributes into a unified 3D scene graph that encodes object relationships within the environment. We use large language models, including GPT and Gemini, to classify object instances and leverage 3D point cloud data to construct the scene graph. This fusion step is central to our pipeline. By jointly reasoning over language patterns and the scene graph, the system can infer the object the expert is referring to. Finally, we generate an AR visual indicator that highlights the expert's intended referent. Through an elicitation study where one remote user verbally described a target object to another user over Zoom, we identified 5 common verbal referencing patterns used to indicate the target. First, direct feature references focus on the object's descriptive attributes, such as color or appearance. For example, a speaker might say, "the black thermos," using intrinsic features to uniquely identify the object. Second, relational references describe the target in relation to another object in the scene. Instead of naming the object directly, the speaker might say, "the object to the right of the thermos," grounding the reference in spatial relationships. Third, memory-based references rely on prior interaction history. Here, the speaker refers back to something previously mentioned, such as "the one I mentioned earlier," assuming shared conversational context. Fourth, chained references combine multiple patterns. A user may blend descriptive and relational cues, for example, the black thermos below the box, to progressively narrow down the target. Finally, deictic references use pronouns like that one over there, which depend on additional cues such as pointing gestures or shared visual context. On their own, these expressions are ambiguous and require support from other signals. These 5 patterns characterize how people naturally refer to objects during remote verbal guidance, and they inform how our system interprets spoken instructions. However, deictic patterns rely on other patterns or another embodied cues, such as pointing gestures or gaze. Thus, we rule this out from the scope of our research. Using these 4 verbal referencing patterns, we design a scene graph that represents both the spatial relationships between objects and a form of interaction history, which we treat as object-level memory attached to each node. When a user provides a verbal instruction, an LLM agent parses the linguistic attributes of the utterance. It identifies the target and any anchor objects and classifies parts of the expression according to the referencing patterns. These parsed attributes are then mapped onto the scene graph, binding linguistic metadata to the underlying 3D spatial representation of each object. Then, with another agent, we traverse the graph to resolve ambiguities and identify the intended referent. Through this process, the system performs speech-based object referencing and disambiguation in a structured, graph-driven way. Here is a live demonstration of speech-to-spatial. In this demo, we showcase 4 types of spatial language patterns to illustrate how the system identifies a target object from spoken input. For demonstration purposes, we assume that the verbal query is coming from a remote expert. Imagine a scenario where the expert first wants to identify objects in the scene to assess the situation. For example, the expert might ask, "Can you show me the blue object to the left of that water bottle?" Our system parses the descriptive and relational cues and disambiguates which object is being referenced. Similarly, if the expert says, "the rectangular object next to the glasses," the system again combines object features and spatial relationships to resolve the intended target. This demonstrates how speech-to-spatial supports natural spoken instructions and maps them to precise object references in the environment. We can also resolve references that rely on prior interaction history or memory-based cues. For example, the expert might say, "the snack next to the reflective surface object we mentioned earlier." Because the system stores interaction history in an object-centric scene graph, it can refer back to previous mentions and infer that the target object is the chocolate chip cookie. In this second example, the system can localize the referent even when the instruction relies primarily on prior memory, with minimal additional spatial description. The system can also resolve references that directly describe the target with minimal descriptions. In this case, the user refers only to the object's intrinsic attributes or features without relying on any anchor object. Even with a short description focused purely on the target itself, the system can match those features and identify the correct object. Lastly, the system can interpret references that combine multiple spatial language cues to indicate a single referent. Speech-to-spatial parses these ambiguous patterns of human speech into a more understandable format and provides AR-based visual guidance that highlights the intended object. When ambiguity remains unresolved, even after graph-based reasoning, or when there are conflicting conditions, the system switches to a fail-safe mode. In this mode, it falls back to a transcription interface and defers the final decision to the user by presenting the interpreted speech as text. For example, if there are 2 Cheez-It snacks on the table and the instruction lacks relational cues, such as to the left or right of the umbrella, the system cannot uniquely resolve the reference. Instead of making an incorrect guess, it asks the user to clarify through the transcription view. Please refer to our paper for more details. We appreciate your interest in our research. Thank you.